Good evening, everybody. I am Sarthak Raj. I am a second year student at IIT Bombay pursuing my BTech in civil engineering. And today I am here to present my project, which focuses on the design and development of autonomous underwater vehicles for low frequency ambient noise validation. In the oceans, ambient noise is a complex combination of natural and anthropogenic noises caused by wind, precipitation, shipping, and exploratory activities. We classify we classify ambient noise into frequency bands, and for our purposes, we'll be focusing on the low frequency band. There are basically natural and anthropogenic sources of noises, and commercial sonar technology is ineffective in tropical regions. So getting more complete noise maps is challenging. There have been mathematical models which are created and involve the training of neural networks using partial data to generate complete noise maps. AIS data has also been used to generate shipping noise maps in various tropical regions worldwide, but we require a custom solution for Indian Ocean region to validate such mathematical models. So boats and diver operated hydrophones are obviously limited by human capacities, which are overcome by remotely operated vehicles and autonomous underwater vehicles. AUVs provide an advantage over ROVs because they can be operated autonomously and remove the need and the risk of tethers. They can also venture to deeper regions with ease to provide a more comprehensive noise map. So, what is an AUV? An AUV is an unmanned submersible vehicle that requires no real-time input or control from a human operator and therefore drives autonomously. They have many uses, and acoustic measurements is one of them. They can find shipwrecks, they can explore area, they can map the bathymetry, as well as localize noise sources by deploying hydrophones in clever arrangements. When it comes to AUV design, there are three main subsystems that we focus on, that are the mechanical, electrical, and software subsystem. I will be talking about these in greater detail. In the mechanical subsystem, our main design concerns are the buoyancy of the vehicle. It must be positively buoyant so that in case of failure, it can naturally rise to the surface. It must have 6 independent degrees of freedom for control over its navigation. It must be stable, and the drag calculations must be taken into account. As far as the propulsion system is concerned, the propulsion happens using thrusters and propellers. And using 6 independent thrusters, we can gain 6 independent degrees of freedom for motion. The drag and power consumption must be calculated so that the thrust that is provided by the thrusters can equal the drag that is experienced by the vehicle as a whole. As far as the shape is concerned, for our purposes, non-torpedo AUVs provide a greater control at the cost of maximum velocity. Since hydrophone sensing does not require movement at high constant velocities, this offers us greater freedom. It also provides a greater choice for hull design, therefore increasing the modularity of the system. The types of hulls that I've previously mentioned are the main hull, which can provide a waterproof vessel for the main electronic stack, including the onboard computer. Battery enclosures, which are attached so that they can be easily accessed for removal and replacement. IMU stands for inertial measurement unit, which uses the magnetic orientation of the Earth. It requires a special hull made out of non-metallic materials to prevent shielding. And camera hulls, which are designed in-house so that cameras can be provided access in the forward direction as well as below the submarine. The assembly of the vehicle happens on a main frame on which hulls are attached. Placement of some hulls should be done at particular positions like cameras in the front and at the bottom. Electronics that are housed in various hulls are connected through neutrally buoyant cables which are weaved through penetrators. The most important aspect of the mechanical design is the waterproofing of the vehicle. It is essential for the protection of electronics, as at high depths, even a small amount of leakage can cause catastrophic failure. The end caps that are placed on the vehicle must be waterproofed using the O-rings in accordance with the Parker handbook. Special attention must be given to penetrators because they can be likely points of failure. We will move on to the electrical subsystem. There are basically the main components of the electrical systems are the power source, the computer, the GPU, and the electronic stack. The following flowchart tries to provide a flow of control for the electrical subsystem. Basically, it's divided into multiple modules which perform their own specific purposes and are connected together by the CAN bus. The CAN bus allows intercommunication of said modules as well as communication to the software stack, that is the GPU and the SBC. Let us talk about the battery management system. A battery cannot directly be connected to an electronic stack because it may suffer failures which can be catastrophic for the system. A BMS is designed to allow the efficient discharge and management of the battery. It measures the state parameters like temperature, discharge rate, state of charge, and state of health. It also implements features like battery hot swap and cell balancing, which allow us to utilize the battery to its maximum capacity. Not all components will operate at the same voltage that the battery provides, so regulation must be done. This is done by the power distribution system. Common voltages like 12 volts, 5 volts, or 3.3 volts will be generated upon separate rails. The current requirements need to be taken into account. Additionally, digital switches like MOSFETs can be installed to provide a way to turn components on and off by using software to allow or cut off power. A GPIO pin on a microcontroller unit has no predefined usage as they can be modified during runtime. For us, they will be used to establish control from a higher layer, that is the software system, to the rest of the AUV. The SBC communicates with the GPIO using USB or controller area network. GPIOs are commonly implemented by using ICs or microcontroller units. Additionally, GPIO systems are also responsible for generating pulse width modulated signals for analog control over thrusters. Apart from all of this, certain emergency protections need to be provided up to all the boards. These are the overvoltage protection, the current surge protection, and the reverse polarity protection. The overvoltage and reverse polarity protection need additional circuitry to be implemented, but the current surge protection can be implemented directly via a fuse. Now we will talk about the software subsystem. The following flowchart tries to provide an overview of the software architecture. I will briefly describe it. Data is gathered via drivers from the various sensors like the IMU, the DVL, and pressure sensors for localization. The data from cameras are used for vision, and the data from hydrophones are used for acoustics. All of this data is provided to the control system as well as the navigation system. The control system is responsible to implement the algorithms that are provided by the navigation system by implementing PID loops to provide the necessary power to the thrusters. It sends its data through the CAN bus to the electronic stack, which then performs the necessary actions for the thrusters. The navigation system itself tries to provide a path between 2 points A and B, and it tries to calculate that path so that the AUV does not face any collision. The mission planner is basically the brain of the software architecture, and it allows for various features which we'll talk about later. So drivers basically input data from various sensors and publish it to robot operating system. So localization, as I've previously mentioned, is done using IMU, DVL, depth sensors, and altimeters for the estimation of position, velocity, acceleration, and the orientation of the vehicle. The control system basically takes into account a set point input that is given by higher layers and uses proportional, integral, and derivative control loops to output what torques and forces are required by the thrusters to bring the vehicle into a specific orientation. The control system allocates power by sending signals from the SBC through the CAN bus. Vision is implemented using cameras. This is parallel to localization and control for dynamic variables. The data from the cameras must be taken as input to implement computer vision algorithms to identify objects that the AUV encounters. Using ML techniques is advantageous in certain situations where the water is not relatively clear. This is the perfect case for turbid lakes and ocean water, as custom calibration need not be done for every single environment. However, training the CV algorithm itself can be very resource intensive. Another challenge that the cameras face is that at high depths, vision is not a very reliable source of information. So the main navigation system of the AUV rests with the hydrophones. Speaking of the navigation system, it is utilized in the often complex and rough bathymetry of the oceans and can calculate efficient paths like circles, ellipses, and pathological curves as well. Now about the mission planner. It is the top layer of the software subsystem, which runs over the software stack and acts as the decision maker of the vehicle. It stores that the tasks that the AUV is designed to perform, whether there are any prerequisites to the task, how many times the task should be attempted, and whether the task was a success or a failure. This can allow us to implement some form of intelligence in our system. As in, if it fails too many times, it can simply skip that task and therefore avoiding the error that it is stuck on that specific task for long. Now we'll be talking a little bit more about the hydrophone module and the underwater noise. So when hydrophones pick up acoustic signals, they not only pick up the ambient noise, which is our useful signal, they will also pick up self noise that is generated by the hydrophones, as well as vehicle self noise generated by various components like the thrusters. Now the self noise parameters must be minimized and denoised to get any useful signal. And standards basically suggest that the weakest ambient noise signal must be at least 6 decibel greater than the cumulative self noise. Regarding hydrophones, there are two kinds of hydrophones which are mainly available. The first one is the acoustic scalar hydrophones, which basically estimate noise level using omnidirectional pressure sensing. These are only designed to measure a scalar quantity, that is pressure. Acoustic vector sensors, however, also measure directional particle velocity apart from noise levels to measure acoustic intensity, which is a vector quantity. Due to this ability, it has been proven to provide hardware advantages over scalar sensors, as in localization algorithms need a fewer number of vector sensors to implement. Talking about arrays of hydrophones for localization, swarm robotics, which basically involves multiple AUVs, each fitted with hydrophones, they are deployed. Swarm or leader follower algorithms are utilized for the localization of noise source, path planning, and navigation. This is ideal in the scenario that the AUV is small and relatively inexpensive to build. If our AUV design is large, towed hydrophone arrays might prove a better option. It's basically a cable with equidistant hydrophones that is stored by the AUV. Higher resolution images can be obtained by interpolating the hydrophone array data. So far, after my project, the progress that has to be made is the CADing and analysis of the vehicle, iterative designs to determine the structural integrity, CFD stability, and thermal dissipative capacity of the current design must be established. The PCB design, programming, and assembly of the electrical stack in accordance with the control flow provided should be executed. Then the implementation and maintenance of the software stack code base for various components like the mission planner, navigation system, control system, and the device drivers must be executed. And finally, and the implementation of a noise source localization algorithm using an array of hydrophones and the necessary changes in the electrical and mechanical subsystems must be taken forward. With this, I come to the end of my presentation. Thank you.